Okay, so let's recap and finalize this problem. If I look at both of them here on the right side, basically at 1, the slope is like a positive 1, and that's why the purple derivative function has a y value of 1 there. If I look at somewhere over here like 4, notice the slope is less steep, like a half maybe. I know that also from the function that I found algebraically. And if you notice, the purple function at 4 has a value of a half. If I go further this way to the right, it gets even smaller to something like maybe a third. If I were to look at the slope of that little triangle, and notice the y value is about a third when I'm at maybe an x value of 9 or so. And when I come over here near the origin, it gets really, really steep and completely vertical, and that's why the y values here of my derivative keep getting bigger and bigger and bigger. Now let's go look at another example where I don't have the actual function to use the algebra on it to come up with the derivative. We can just analyze it graphically. So again, this is my function, and I don't have a formula for it given for me to go do my f of x plus h business. So we're just going to try to guess, maybe underneath it, what the derivative function may look like just by walking around the entire blue curve and figuring out ideas of what the slope might be. So again, it's pretty obvious that at 0, the slope is 0. So at 0, my y value for the derivative would be 0. Notice if I look at the right, I have, it looks like a negative slope, still a negative slope, negative all the way across. They're negative slopes, and they tend to become flatter and flatter as I go to the right. If I'm just focusing on the right, all the slopes are negative. At some point, it's an absolute value the biggest, and then they keep getting flatter and flatter and flatter. And if it's getting flatter, the slope of the tangent line is approaching 0. So if I had to guess underneath what's happening from here, I'd say there's some negative values, and then those negative values, notice they're getting flatter and flatter, and they have no choice but to go and become and approach the y value 0. So maybe my guess would be like something like that for the right side of that graph. And by symmetry, notice on the left, these are all positive slopes that I'm looking at, tangent line slopes. And again, at this end, it's also flatter, and it approaches 0. And there's symmetry going on too, so the same type of slopes that happen on the right happen on the left, but they're all positives, and then they become 0. So maybe something like that is what my derivative would look like. So again, I don't have the function itself, I'm just guessing what the derivative of the original function, the graph given, might lead me to and what it may look like. Now let's go recap everything regarding a function having a derivative and talk about when a derivative may or may not exist. So a function is said to be differentiable, that's the terminology we use, at x if its derivative exists. Remember, we use this backwards e for existence, exists there. And a function is said to be differentiable on an open interval ab if for every single point in that interval the function is differentiable. So at each little x I go to, that difference quotient limit exists. That means in an entire interval the derivative exists. Now sometimes the domain of the function itself compared to its derivative may vary. If we go back to our previous example, the square root function we looked at, notice this function has domain x greater or equal to 0 because it's defined at 0 also, versus its derivative whose domain is x only greater than 0, because notice it seems like there's a vertical asymptote here, and I don't have this function defined at 0. Notice it becomes undefined there. So it's possible that the domain of the derivative will actually be sort of quote-unquote smaller and contained in the domain of the actual function. Now the reason that that is not included there is because the derivative becomes undefined there. So let's go talk about the existence of derivative. Now, when does a derivative exist or not exist? Well, logically, if you just think it through, based on how we know the derivative is defined, f is said to be differentiable at a certain point a if this limit that we were analyzing actually exists. And we know when limits can exist or cannot exist. You know, for example, if you go from the left and right and it's not the same, then the limit doesn't exist there. So for every point in that interval we're talking about this limit exists, then we're good, the derivative exists. Otherwise, it does not. So of course, if that limit doesn't exist, we say that it is not differentiable at that point, x equals a, or maybe throughout an entire interval. Let's look at the 3 common cases where a derivative may not exist or does not exist. So one thing that could happen is you could have, let's visually talk about it. You could have a graph, and at A, maybe you end up with a sharp corner. So we'll call this the sharp corner case. And we'll look at it in more detail algebraically also. But in the sharp corner case, what happens is when you analyze this difference quotient limit right here at that point, the left-hand limit and the right-hand limit don't end up being left-hand limit, will not be the same as the right-hand limit, and therefore that limit won't exist. And we'll say, well, if that limit doesn't exist, it's not differentiable there. That's one thing that visually could happen. What's the second thing that could happen? The second thing that could happen is that basically the curve doesn't have a sharp corner, but the tangent line ends up looking vertical, kind of like that in the square root example we just saw. If this is the point of interest A, notice what happens is if I take a nearby point and I look at the secant line and I keep moving it closer and closer and closer, eventually that tangent line becomes vertical, like it did in our previous example. And when it becomes vertical, of course, the slope becomes undefined and m goes to infinity. And we say this difference quotient highlighted in yellow will not exist there. So again, why does that happen? Notice if I pick a point here and I move it closer and closer, it's looking more and more vertical. And if I pick a point down here also, move it closer and closer, that tangent line at that point is completely vertical. Remember, that's an undefined slope. And the third case is the obvious case. You know, you could have a graph that's discontinuous. And if it's discontinuous, the derivative is not going to exist at that point because obviously the left-hand limit in this difference quotient in yellow will not equal the right-hand side limit. So the derivative will not exist there because of the discontinuity. So the 3 classic cases are visually, if you see a sharp corner or a place where you feel like the tangent line is becoming vertical, or a discontinuity, you automatically know that the derivative does not exist at that point and that the function is not differentiable at that point. So visually, if a function is differentiable at a point, that means that if I zoom in my camera or graph or whatever at that point, the graph should act linear there. And we come back and revisit this idea when we do linearization of a function. If you look at the 3 cases, if I zoom in my camera on this guy, when I zoom in, that sharp corner will always remain sharp and never become linear. Same thing here, if I zoom in my camera here, the 2 pieces are disjoint, they're never going to appear linear. And if I zoom in my camera here, well then it will appear linear, however it'll be a vertical line with undefined slope, hence the derivative won't exist. Let's go look at our TI calculator that actually zooms things in for us and see what I mean. So one function that we know that has a sharp corner is the absolute value function. Let's go to second 0 and push enter to choose the absolute value function. Let's go look at the absolute value of x, and I'm going to go to a zoom standard window. And there's what it looks like. Now I'm going to go keep zooming in the center. So I'm going to do a zoom in. So zoom in would be number 2. It's blinking at the origin. I'm going to push enter. There it is. I zoomed once. I'm going to zoom again at the origin. I'm going to zoom again at the origin. And notice how many times I zoom in, it's just remaining a V. It's not looking linear. That's how I know visually that that function is not differentiable at 0, because it keeps having a sharp corner, versus something like, let's go look at our x squared function, or the square root function would be the same thing. If I do a zoom 6, let's say I want to zoom in at 1, 1 right here. If I go to zoom 2, and is this thing differentiable at that point? If I go there and I do a zoom, oops. So I went to 1, 1 and I'm going to push enter to zoom in. If I zoom again, zoom 2, enter, notice it's becoming, zoom 2, more and more linear. The function is looking linear, no sharp corners can be seen. That's how I know it's differentiable throughout the entire curve, because the more I zoom in, the more linear it's going to look. Let's go look at this other function, a cube root function. So I'm going to go to math, and I'm going to go to the cube root. And let's do cube root of, I don't know, x, let's say x minus 2, make it at least different than the origin. And if I do a zoom 6, a regular graph, notice right here where the twist happens, that feels like that may not be differentiable because the tangent line may become vertical there at that point too, but let's go zoom in and see what happens. So I'm going to do a zoom 2, and I'm going to go near that point. And there's the first zoom. I do one more and we'll get a pretty good idea. Notice what's happening. If I zoom again, notice how it's looking pretty much vertical, and it's not differentiable there because the slope of the tangent line becomes undefined. So again, for the first case, we looked at the absolute value function and saw it didn't act linear as we zoomed in. For the second one, we looked at this cube root function. And for the third one, again, that's pretty self-explanatory. It's a discontinuity. The limit from the left and the right won't be the same when I analyze this difference quotient. Now let's go quickly look at the absolute value function algebraically and look at this actual limit definition and see what happens. All right, so we know it's not differentiable at 0. We saw the picture, it had a sharp corner. Let's go look at the definition of the derivative and see how it gets failed. So since we're interested at that point 0, we're going to go look at the definition of the derivative. At 0, a would be replaced with 0 because we're interested in 0, and we're just going to actually go plug that into our function. This should be 0 because a is 0 here, so f of 0, and so 0 is gone, f of h minus f of 0 over h. Let's go plug it in. So we ultimately get to the limit as h goes to 0 of this guy to analyze. Now we know what the definition of the absolute value function is, and in trying to analyze this limit, let's go towards 0 from the left and the right. And if I do that, I know from the left, I am going towards 0 from the negative side, so this is absolute value of h. So absolute value of h gets replaced with negative h because that's what it is from the left of 0. And that we know is equal to negative 1. And we know on the right, when I go to 0 from the right, they're all positive values, so it's just an h that I'm dealing with. So absolute value of h gets replaced with h, and I have h over h, which is just 1. Notice the left-hand limit at 0 is not equal to the right-hand limit at 0, therefore it's not differentiable at 0. And so basically, to recap, what we did was we had the definition of the derivative algebraically to show and prove why it's not differentiable. We went to that, we replaced all the a's with zeros because we're interested at 0. And in trying to analyze this limit, we realized that that limit of the difference quotient doesn't exist. So if the limit doesn't exist, then f prime of 0 doesn't exist. Next, we have the idea of how continuity and differentiability are connected, and we'll talk about that in the next video.